Have you ever just looked at a glacier and thought, how? How can something that's basically a mountain of solid ice flow? It just seems to defy logic, right? But they do. They move. So today, we're going to dive into that incredible paradox, the slow, powerful, unstoppable movement of the world's rivers of ice. And I mean, you can see why. Just look at this. It's so easy to see why we call them rivers of ice. This one, here, carves right through the valley, looking for all the worlds like a river that just froze solid mid-flow. But here's the thing. It's not frozen in place. Not at all. It's moving, even as we speak, just so incredibly slowly that our eyes can't pick it up. So that really is the million-dollar question, isn't it? This isn't water, it's solid, crystalline ice. How on earth does it manage to move downhill, carving up entire landscapes as it goes? Well, believe it or not, the answer doesn't start with a mountain of ice. It starts with a single, tiny snowflake. Yeah, to really get how glaciers flow, you first have to understand what they're made of. And a glacier isn't just a big pile of ice. No, it's the result of this amazing transformation that takes hundreds, sometimes even thousands of years. It all kicks off with snow, lots and lots of snow. In really cold places, the winter snow piles up year after year and never gets a chance to fully melt in the summer. So as these new layers build up, the pressure on the bottom layers becomes immense. It literally squeezes the fluffy snowflakes together, first turning them into these dense, sugary pellets we call firn. You can kind of think of firn as the awkward teenage phase between snow and true glacier ice. And check out the numbers here, because this is where it gets really wild. Look at that change in density. You start with fresh snow, which is mostly just air, super light, but by the time it becomes solid glacier ice, it's more than 10 times denser. That's just an incredible amount of pressure at work. And this squeezing just keeps on going. Eventually, all the little air passages between the snow grains get sealed off, trapping these tiny bubbles of ancient atmosphere inside. That's when it officially becomes glacier ice. Oh, and that brilliant blue color you see in glaciers? That happens because the ice is so dense now, it absorbs all the other colors of light, but scatters the blue light right back at you. Pretty cool, huh? Okay, so we have our material, a massive, dense body of ice. Now that it's formed, there's really only one thing left to do: move. And there's a single, relentless force that gets this whole river of ice flowing. Yep, it's that simple and that powerful. Gravity. The exact same force that makes an apple fall from a tree is what's pulling trillions of tons of ice downhill. The sheer weight of the glacier is enough to make the ice itself start to deform and flow. Now, this flow happens in two main ways. The first is called internal deformation. Deep down inside the glacier, the pressure is so intense that the actual ice crystals can shift and slide past each other, letting the whole thing kind of ooze. The second way is basal sliding. This is where the entire glacier slips and slides over the ground on a thin layer of meltwater, which acts like grease. I absolutely love this analogy because it makes it so easy to picture. Think of the ice crystals as a deck of cards. You can push on the top card, and each card below it slides just a little bit. The deck changes shape, but it's still a solid deck of cards, right? That's exactly what's happening inside the glacier. It's how a solid can literally flow without breaking. So when you put it all together, a glacier's total speed is a mix of that internal card shuffling and the whole thing sliding along the bottom. This diagram shows it perfectly. Right at the bottom where the ice is scraping against rock, there's a ton of friction, so it barely moves. But as you go up, you've got that internal flow kicking in, plus the whole thing is sliding. The end result? The ice at the very top of the glacier is moving the fastest. What you get is this incredible, massive conveyor belt system. Snow falls and becomes ice way up high in what we call the accumulation zone. Then gravity, our engine, transports that ice downhill to the warmer, lower elevations, the ablation zone, where it eventually melts or breaks off. It's this beautiful, continuous cycle: accumulation, transport, and finally, loss. But you know, this colossal movement isn't perfectly smooth. The ice is under unbelievable amounts of stress, and just like anything else under that much stress, sometimes it breaks, and this is where we get some of the most stunning and frankly dangerous features of any glacier. We're talking about crevasses, See, while the ice deep down can flow and bend under all that pressure, the top layer, say the first 100 feet or so, is much more brittle. So when the glacier speeds up or stretches over a bump in the landscape, that brittle surface ice just cracks wide open, forming these massive, deep fissures. And what's really fascinating is that not all crevasses are the same. Their patterns tell you a story about what the ice is doing. If you see cracks going across the glacier, that means it's speeding up and stretching out. If they're running along the direction of flow, it means the ice is spreading sideways. Each type of crack is a clue, helping scientists read the glacier's movement. I mean, just look at the surface. When you see a glacier that's this heavily crevassed, you really get a visceral sense of the power we are talking about. These aren't just cracks in the ice. They're the scars left by a mountain of ice literally tearing itself apart as it grinds its way down a valley. And all that grinding and tearing does a lot more than just move ice around. As glaciers flow, they become one of the most powerful forces of erosion on the entire planet. They completely reshape the world underneath them. Seriously, think of them as Earth's giant bulldozers. They pick up rocks and boulders and use them like cosmic-grade sandpaper, just grinding away at the bedrock below. They take sharp V-shaped river valleys and carve them into those huge, sweeping U-shaped valleys you see in places like Yosemite or the Alps. They are, without a doubt, nature's master sculptures. So, it's clear these slow-moving giants have sculpted our planet's past, but they are also absolutely critical to our planet's present and, of course, its future. Let's just sit with these numbers for a second because they're mind-blowing. Glaciers hold about 68%. Let me say that again, 68% of all the fresh water on Earth, over 2/3. And the two big ones, the ice sheets in Antarctica and Greenland, they account for 99% of all that glacial ice. And for millions of people around the world, the meltwater from these glaciers is what fills their rivers and provides the water they need to drink and grow food. And that brings us to what might be one of the most staggering numbers in all of climate science. If the Antarctic ice sheet, the single largest mass of ice on Earth, were to melt entirely, it holds enough frozen water to raise global sea levels by 80 meters. That's nearly 260 feet. Just let that sink in. So that brings us right back to where we started. We've seen how these incredible rivers of ice are born, how they flow, and how they've literally carved the world we live in. For thousands of years, they've been this powerful but relatively stable force of nature. The urgent question we're all facing now is, what happens when these slow giants start to move and melt faster than they ever have before? How will that shape our future?